Hello, welcome back. In this video, we will try to understand PCA. So, this is going to be the outline of this video. So, first, we will discuss what is PCA. Then, we are going to uh, understand why we need PCA. And finally, we are going to have an intuitive and mathematical understanding of PCA. So, PCA is basically principal component analysis. Throughout this video, we will use the short form PCA, and also we are going to use PC as principal component. So, as you know, it is a technique to reduce the dimensions of data. So, PCs are going to be the new dimensions of the data. So, let us now jump onto the first section of this video. What is PCA? So, as I say, PCA is nothing but an algorithm for linear dimensionality reduction. And then what it is doing, it tries to reduce the number of dimensions while preserving as much information of the data as possible. So basically it is an optimization. Why I say optimization? Because there is two things here: information of the data and then these dimensions, and these are correlated in some sense. Like if you decrease the dimensions, then your information of the data is also going to decrease. But we want to decrease the dimensions while keeping the information as high as we can. So this is an optimization, and we are going to see how we will try to optimize it and preserve maximum information while decreasing the number of dimensions. Now, this is very important to know. Do we need additional pre-processing of data before applying PCA? So the first one is like, what are the requirements to apply PCA? We must have numerical data. So PCA is applicable only on numerical data. And now 2 and 3. This is one. 2 and 3 are not required but recommended. So we do the mean centering of data. In later half of this video, I will also explain why mean centering is not a required but recommended thing. And then the last one is standardizing. Sorry. So the second and third is not required, but these are recommended. The third you can simply see because PCA is going to use the covariance of data. And as you know, covariance, what is covariance? Covariance is nothing but So this is nothing but the relation between two dimensions of the data. So this is the mean in x direction, this is the mean in y direction, this is the y direction value of some dimension, and this is the x value of another dimension, and we are trying to find the covariance. So let us say if the scale of y is much higher than the scale of x, then in that case you are going to ignore, or like this process will ignore these values. So if this is very high, this is very low, then the process will ignore the information coming from x. So we need to have these two data on the same scale, and that is why it is recommended to have the dimensions on the same scale. So now let us move on to the next part of this video, and in this part I will explain why do we need PCA. So why are we actually applying PCA? The sole purpose is PCA is applied to reduce the dimensions, right? So dimensions must be a problem. High dimensional data is a problem. So we will now see problems associated with high dimensional data. So the first problem is that it is hard to interpret. So if you have high dimensional data, the interpretation of that data is going to be very hard, or you cannot interpret that high dimensional data directly. So we need to reduce the dimensions for that. And second one is like visualization of data is not possible when we go beyond 3D. So if you have the data in 1D or 2D or 3D, then you can definitely do some kind of plotting and see how the data is distributed. But when you have dimensions more than 4D or 3D, you are going to have a difficult time to visualize that data. Then the third one is like the storing of the data is expensive. So when you have high dimensional data, that means it requires high storage to store that data. Let us say you have earlier 10 dimensions, and now you want to reduce that dimensions to 4, or let us say you want to reduce that dimensions to 5, and all the numerical data was of the same, like it was using that same data type, floating 32. Then in that case you are reducing the storage capacity to half. So it is that easy to understand that storing of the data is going to be expensive. And finally, the last one is you are going to you are using PCA to reduce dimension so that you could apply some ML algo on the newly projected data. And you are going to apply a new algorithm or maybe some other machine learning algorithm on the newly projected data, and that ML algorithm will be happier to accept data in fewer dimensions, since it will require less computations. So it is that simple that if you are using some a machine learning algorithm in the downstream task, then in that case, that ML algorithm, if you give the ML algorithm a data set with fewer dimensions, then it will do less computations, and the latency will definitely reduce. So if you want to improve the latency of the downstream algorithm, then you can apply PCA to reduce the dimensions. Now here is an example. This is a very famous MNIST dataset. In MNIST dataset, it is a dataset of handwritten digits, and the original dataset contains 784 dimensions. So we have the original dataset with 784 dimensions. And what happens when we project this data to a single dimension, single new dimension? So you see, most of the information is lost. So the image now looks blurry and may not be as good as the original one. And when you increase the pieces, so when you increase the dimensions of the newly projected data, then the information content also increases. And similarly, when you increase the PC to 100, then the information increases more. And finally, when you have PCs 500, the information from the original and the PCs 500 are almost comparable. So here what you see, we have 784 dimensions, and when we reduce this to 500 dimensions, we have information loss, and we have dimensions reduced, but the information loss is very less comparable to what we gain by reducing the dimension. So we, as we discussed, we have many good thing about reduced dimensions, and if we could reduce the dimension with a very little information loss, then we are happy to reduce those dimensions. So this was an example, and now let us jump on to the next part of this video, where we will try to understand the PCA in an intuitive way. So let us say we have given data of n rows, and the original dimension of data is d. So I will write the initial state of data and then final state of data. So this is the given one, and then what we want to achieve using PCA. So initially we have d dimensions, and we want to achieve m dimensions. And note that this m is going to be lesser than or equal to d. Not if we apply explicitly PCA, then we do not want to have similar number of dimensions, but mathematically we get equal number of PCs. So we will write mathematically like this, that m is less than or equal to d. Now you see, this is the initial, this one is the initial case where we have d-dimensional data, and these are the data points. We have n number of rows. So when we finally use the PCA, we want to reduce the data in m dimensional form. This m is less than d, and we have n number of data points. So what is going to be our strategy to reduce the dimensions while preserving the maximum information we have? So we will now link how PCA is linked with the variance of data. So as you know, we want to preserve the information content of data, and information of the data is directly linked with the spread of data in space. So I will give you an example. So let us say you have data in a space, and another data in space. So definitely if the data is spread in this space, and if you have a data which is centered at some part of a space, then definitely this data contains more information and more valuable for your ML algorithm to understand the underlying pattern. But this data is not good for your ML algorithm to understand the underlying pattern. So we definitely want to have this kind of data, the first type. So we can say that a spread of data in a space is accountable for the information content of the data, and the spread of data is characterized or can be seen as the variance of the data. So a spread of the data is directly linked or connected with the variance of data. If we have high variance of data, that means the data is more spread. So definitely if we want to preserve the information content of the data, we need to preserve the variance of the data onto the new dimensions. So now let us move onto the onto one example which shows that how variance is determining the information content of the data. So let us say we have we have this given data with two dimensions. So f1 and f2 are dimensions of this data, and you can see the data is spread more onto the f1 dimension than f2. What happens when we try to ignore one of the dimension? So let us say in first case we are ignoring f2. So we are ignoring this data, this dimension. So every data point will be now projected onto f1. So if we project this data point on f1, then this comes the result. And we have case 2 where we try to ignore f1. So when we ignore f1, so every data will only have its f1 coordinate, and then this will be the case where we have data which is a very uh, like it is congested data, and it is not having much information as in case 1. So we definitely want to have the data uh, spread on f1 rather than f2. So when we try to reduce this dimension, we want to opt f1 as the correct dimension, which preserves more of the information. So this is how PCA works, but this is not the mathematical way how PCA works. But I want to say that PCA also want to preserve maximum variance of data. So now let us move on to the next part where we will introduce the perspective of variance. So let us define the problem again. So we have data points x1, x2 till xn, and these are all d-dimensional data set. Sorry, these are all d-dimensional data set, and I will also write that. And we want finally to convert it to m-dimensional data set. So let us see this example where we have these data xn, and now we assume that this is the first PC, this is the basis vector on which we will be projecting our data. So this is going to be our first PC, PC1, because it tries to capture the maximum variance of data. So when we project xn on this PC, and we are going to see how we will do it, but in the next section we will prove it mathematically. In this section, let us also try to formulate the assumptions of our PCA. So The assumptions are going to be that mean of data will be kept as 0. So this is the only assumption we are using for the mathematical formulation of PCA. So, and also let us say that we have a matrix. So this is a linear transformation matrix. So what it will do, it is a D cross M matrix. So you can imagine a D cross M matrix which will try to project the data onto the lower dimensional space. So when you apply BT into Xn, it will project the data onto the low dimensional space. We will use it, but we will have some simpler understanding of this. So now let us prove why the mean has no effect on the variance of projected data. And let us first assume that mean of original data was mu. So in this section, we will try to do the mean centering of data whose original mean was mu. And we will understand why even if we do the mean centering, there is no effect on the calculation of PCs. So now let us recenter the data using the mean mu. So recenter the data with mu. So every x will be recentered. So this is how the points will look like after the mean centering. So and then we have so now let us calculate the variance. So now let us calculate the variance of mean centered data. So what we did, we performed the mean centering in step 1, and in step 2 we are trying to find out the variance of this mean centered data. So we will write it like that: variance of G, which is uh, the new dimension, and we will project this mean centered data onto the new space. So what we did, we projected the data which was the original data x onto the new space, where we want to have only m dimension. So from d dimensional space to m dimensional space we are projecting the data, and we want to find out the variance. So it could also be written as, when we expand it, we can write it like this one. And if there is some kind of addition, or we want to subtract something, in that case variance of a plus b or a minus b could be written as variance of a plus variance of b. So it is as simple as that. We will apply this rule here. So variance of bt x minus variance of bt mu. Now you see, this mu is a constant. So you are just projecting a constant on some new dimension, and it will again be a constant. So when you try to capture the variance of a constant, it is always going to be 0. So variance of this will be 0 because it is a constant, and this term will remain. So what it means, that variance of the data on the new projected dimension is always going to be the same as the variance of data without mean centering. So what we proved here, that variance of the data onto the new projected dimension is equal to the variance of data without mean centering. And also what we started with the variance of the newly projected data with mean centering. So everything is equal. It means even with mean centering and without mean centering, the variance remain constant. So it doesn't affect the variance of data even if we do the mean centering of the data. So that is why we can do the mean centering of data. Now let us move to the mathematical understanding of PCA. So here, now let us move to the mathematics part of PCA. So let us first introduce the conventions that we are using. So you see here, this is xn. So xn is nothing but the nth data point. This is original nth data point. And then uh, we are using currently two dimensions just for example. And this b1 is the basis vector 1, principal component 1. And then we have so yeah, these are the only naming conventions we have. These x1 and x2, these are the dimensions of original data. Now let us try to project this xn point to this new dimension, which is our basis vector. This is going to be our principal component 1. So we will first project this xn onto this b1, and let us see how we can project it. So we will call it, so we will call it b1n. b1n is equal to b1 transpose xn. So this is how we can write b1n, which is the data point when projected onto this new basis vector, onto this new principal component. And what is b1? What is b1t? So b1t is nothing but cos theta and sin theta. Since we have taken this b1 at some theta, we can always write a vector in terms of r theta. So we can always write a vector in terms of r cos theta, r sin theta, and where r is magnitude and theta is direction. And since we have kept the magnitude of this basis vector as 1, I will try to explain why we have kept r is equal to 1. But for now, let us take this as 1. Then in that case, we can write b1t as cos theta and sin theta. And then we have this xn, which can be written as x1n, x2n. So finally, we have this b1n is equal to x1n cos theta plus x2n sin theta. And mathematically, we can also understand this using geometry. So now I will explain it how. So this one is the b1n that uh, we are trying to find out. And this b1n, if xn is here, then this b1n can be written as this one becomes the x1 cos theta, because this one you see is x1n and this is theta, so x1 cos theta is this one, this value. So we have this part as x1 cos theta, and then you see this part, the rest of the part, which makes up b1n, x1n cos theta plus x2n sin theta makes b1n. So this part is basically x2n cos theta. And where is this coming from? So you can directly get it from this, follow this yellow one. So this yellow line, when projected using this x1 sin theta, it comes to this line. So this is the final projection when you project this line using the sine theta. So this becomes x2 sine theta. So this is the final value of b1n, which comes x1 cos theta plus x2n sine theta. Now let us project all the data similarly and find the mean. So what we are going to do next is, similarly, this was done for the nth data point, and when we try to project every data point, then what we get. So let us try to find out the mean of all the newly projected data points on basis 1, which is b1. So we try to find out the mean, which is going to be like this. So this is going to be the mean, and we replace this b1 with what we just get here. So this is going to be the mean of newly projected data. Now we will further try to get the next steps. So this comes around. So see, this is summation, and we can always split the summation. So we will split it. So now it is easier to evaluate when we have this splitted summation. So see, this cos theta is not dependent on I. So this cos theta is constant once we have this. So we have not found out the theta yet, but this cos theta is not dependent on varying the I. So we will keep it outside the summation. Similarly, this comes. So finally, what we can write? So see, this one and this one is nothing but a constant for now, and this one and this one, sorry, I have written this is sine theta, this is not sine theta, this is x2y. So this is nothing but the, this is now just the summation of xi's and x2 i's. So it is the summation of all the data point in first coordinate system and second coordinate system. So this is the summation of all the data point in original coordinate system. So if we take this n and this all the summation, then this is nothing but the mean of original data in that direction. So we will write this one as mean in x1 direction plus mean in x2 direction. So, and what we assumed, let me recall you. So what we just assumed before starting this problem. So we have assumed this thing, that the mean of the data is going to be 0. So if we have mean is equal to 0, then in that case this part becomes 0 and this part also becomes 0. So overall this becomes 0. So what we got is that average or mean of all the data onto the projected basis is 0. So this is our finding. Now let us take our first principal component, since it has the maximum variance of data on it, and try to maximize that variance. So what we are going to do next is try to project all the data onto this new basis, onto this basis, and then we are going to maximize that variance. That is our purpose, and that is our goal next. So let us do that now. So now I will change the naming conventions, as we have many things to write, so it will be easier if we can define everything neatly. So this is z1n as b1 transpose xn, where n is nothing but 1 to n. It is the data point number, and here 1 is we are writing for PC1. So for PC2 we may write it as B2, and this is transpose, and this one is nothing but the projected value of xn on to PC1. So G1n is when we project the data on the basis 1. Now what will the variance of projected data points? So let us write that. First let us see what is variance, then we will project the data onto the new axis. We have some, okay, we will move this up. So now let us try to see what is variance. Variance is nothing but summation of all points. For all points we try to do x minus mu divided by n. So this is variance, where x is the data points and mu is nothing but mean of the data points, and n is the total number of data points. So this is how we define variance. And now similarly we can find the variance 1. Why we call variance 1? This is variance on PC1, so we are calling it explicitly 1. Summation of I goes from 1 to n, and then this goes like b1 t dot xi minus 0 because mean is 0. And then we can take this in outside here. Yeah, so this is the variance when we project the data onto PC1, and this one, this is coming from here. So we are just trying to put the projected data point and find the variance onto PC1. This can be called as variance on PC1. So we have projected all the data points on PC1, and we are now trying to find out the variance of data point on that PC. So we can further simplify this and write it as 1 by n. Summation goes from 1 to n, and this one becomes, so b1t is nothing but a vector of, sorry, b1t is nothing but a vector of 1 cross d dimension, and then xi is a vector with 1 cross d dimension. And when we try to do the dot product between b1t and xi, it gives us a, a scalar. So when you do the dot product, it gives us a scalar, and there is a property of a scalar. Then when you do the transpose of a scalar, it gives you the scalar itself. So utilizing that, what we will do is we will write this as b1 transpose dot xi into b1 transpose dot xi transpose. So what we are doing, this is a scalar and this is a scalar transpose. Simple. So utilizing this, how we can rewrite variance 1. So variance 1 now becomes 1 by n. Summation goes from I 1 to n. This is b1t xi, and then b1t xi transpose. And you know the property of transpose, if you do the transpose of a dot b, then it opens up like this one, b transpose dot a transpose. And if you take the transpose of a transpose, it becomes a itself. So utilizing these two properties, we can write variance 1 as 1 by n. Summation goes from I is equal to 1 to n, and then this b1t xi, then this xi transpose, and b1. So since b1t and b1 is not dependent on I, so we will try to take this out from this summation. So we can rewrite variance 1 as 1 by n b1 transpose summation of I goes from 1 to n xi and xi transpose b1. So this is the final rewritten form of variance 1. So this is variance of data on PC1. Now we will try to maximize it. What we know is xi is nothing but a column vector, because xi is the original data point. So it is a column vector with the number of rows as d. So there are d, the feature, the dimension of that original data point is d, and when we transpose it, it becomes 1 cross d. So this middle part, this one, is nothing but a d cross d matrix. So you see here, this is a d cross d matrix. This is the original data, and when you multiply this one, uh, let me show it here, that what is this xi dot xit divided by n mean here. So this is nothing but it could be written as so this is going to be somewhat hard to understand, but eventually you will get there and I will try my best. So this is how this part can be written in the form of this. So this is a d cross d matrix. Now you observe carefully what we have written. We are expanding xi. So xi is written here in the form of xi1, xi2, xi3, similarly xin. Sorry, this is not n, this is xit. And when we transpose it, so when we transpose it, we write it like xi1, xi2, xid. And when you try to do this xi dot xi transpose, then this is what you will get, a d cross d matrix is what you get. And we put the summation inside of this matrix. So this is how it goes. And now when you observe carefully, what is it written? So this is nothing but the covariance matrix. And how it is covariance matrix? Let me further simplify. So what is covariance matrix? So covariance matrix is nothing but it could be written in the form of, so let us say we have only two dimensions, x and y, then it can be written as x minus mu x, then x minus mu x, y minus mu y, and this one as x minus mu x, y minus mu y, x, sorry, this is y, so y minus mu y. So this is how the covariance matrix looks if you have only two dimensions. So for simplification, I have kept only two dimensions. So it is a 2 cross 2 matrix. And now what happens, how this covariance matrix will look if you have mu x as 0 and mu y also 0. Since we have kept we always keep the mean of the data as 0, as we have found out, like as we have also proven that. I will again try to recall that one. So see here, we have kept the mean of data in all the dimensions as 0. So the covariance will look like this. And now you see this one, you see this very carefully, you will find that this is the same case. And now this comes out as the covariance matrix. So this covariance matrix, we will write it now as S. So S will be the symbol for covariance matrix. And now let us take this equation for variance 1 now onto the next page. So we can write as variance 1 is nothing but B1 T S B1. I will write it as the variance of data on PC1. And what was our goal? Our goal was to maximize this variance. So we want to maximize this variance. And now if you see this equation carefully, you will find that variance 1, this variance 1 is directly proportional to the magnitude of B1. So as you increase the magnitude of B1, the variance 1 will also increase. And this suggests us that if you make the magnitude of B1 as infinity, then the variance 1 will be highest. So this is kind of a problem, because we do not want to uh, keep the b1 as infinity, and we just want to have the direction of that basis vector of that pc1, where we want to project all the data point and we will get the maximum variance out of it, not with the magnitude of b1 making it to infinity and then getting the maximum variance. So what we will do now, to simplify this case, we can keep the magnitude of b1 as 1, and then in that case we can write it as we want to maximize the variance b1t as b1, keeping a constant. So this is, we want to maximize it and we have a constant. This constant says that the magnitude of b1 is 1, which can also be written as b1t b1 is equal to 1. So this is the constant and we want to maximize this one. So this is a constant optimization problem. So we can now, we have came up to this part, so we will now, we have this final problem where we have to maximize b1t b1t as b1. We have to find some value of b1 when we have this one as maximum value, and subject to b1t dot b1 is equal to 1. So we will now use the method of Lagrangian multiplier, and you do not need to worry about, even if you don't know about Lagrangian multiplier, it is that simple to understand. So how it defines the problem: if you have to maximize a function fx and it is subject to a constant where you say gx is equal to 0, then we can do it using the following steps. So if you follow these steps of Lagrangian multiplier, we can optimize this problem. So let us say you have this, sorry. So let us say you have this Lagrangian can be written as L of x comma lambda. So this lambda is nothing but Lagrangian multiplier. So this lambda is nothing but Lagrangian multiplier, and we write it as Lagrangian of x comma lambda as fx plus lambda of gx. And in second step, we try to do the partial derivative with respect to x and lambda. So we will do the partial differentiation with respect to x and lambda and set it to 0 so that we can find the value of x and lambda. So solve the system of equations that we get when we follow the step 2, and finally we can get the values of fx. So now we have f of b1 is equal to b1 transpose s b1, and g of b1 is nothing but 1 minus b1t. Remember what we had, b1t dot b1 is equal to 1, and when we take everything to one side, then we get 1 minus b1 is equal to 0. So this function becomes our gx. That is what we defined here, gx. So now we will set up the problem according to the Lagrangian multiplier. Lagrangian of b1, since b1 is the vector and lambda, we can write f of b1 plus lambda into g of b1. And now we have this step 1 done, and step 1 we can write it as fb1 is nothing but this b1 transpose s b1 plus 1 minus b1 transpose b1. Now we will follow step 2, where we try to do the partial differential of this Lagrangian function with respect to b1 and lambda. So if we do with respect to b1, then it comes to as b1 minus 2 lambda b1 is equal to 0. For now, you just consider this value. So if you are confused how we did this, how we did the differentiation of this fb1 with respect to b1, where we have b1 as a vector, s as matrix, then for now just take this one as the final value. I will explain how I did that differential. And then in step 2 we do the differential of Lagrangian with respect to lambda, where we get 1 minus b1t b1 is equal to 0. So this becomes your equation 1, and this becomes your equation 2. So now let us simplify this further with the equation 1 and equation 2 that we got. So if you get this equation 1, you further simplify it, you get 2sb1 is equal to 2 lambda b1, which can be written as sb1 is equal to lambda b1. This is very important. And now let us try to analyze this one. So what is s? S is nothing but d cross d matrix, right? And b1 is nothing but a vector. So how this equation is very important. Ax is equal to lambda x, and in this equation a is a matrix, a is a square matrix, and then this x is a vector. This lambda becomes a constant, and this vector is considered as the eigenvector, and this lambda is considered as the corresponding eigenvalue. Why? If you know about linear transformation, then it just says that you have some vector x, and you're trying to transform that vector using some linear transformation, and you get only you get the same vector, like the direction of vector is not changing, it is just getting some other magnitude. So that vector is nothing but the eigenvector, and the corresponding value by which that vector magnitude changes is the eigenvalue of that vector. So we got this one as SB1 is equal to lambda B1, and this suggests that this B1 is nothing but the eigenvector, and this lambda is nothing but the eigenvalue corresponding to that eigenvector, because lambda is a constant. So we have reached our conclusion that SB1 is equal to lambda B1. This means that B1 and B1 is the eigenvector and lambda is the eigenvalue. Now what we wanted to maximize, let's move to that. So let us move what we wanted to maximize. We want to maximize we want to maximize the variance 1, and variance 1 was nothing but b1t dot s dot b1, as you recalled. So and we have sb1 from here. We have, this is important, so let us write it as equation 3. So sb1 is equal to lambda b1 using equation 3. So let us pre-multiply. So if you want to get this value, we need to pre-multiply with b1 transpose. So let us pre-multiply this equation 3, and we get, so when you pre-multiply you get this value, and remember that lambda is a constant, so you can always keep that constant outside of multiplication. So lambda can be taken out from the middle and it will become this one. And what is b1 transpose dot b1 is nothing but what we got in equation 2. So you recall b1t dot b1 is nothing but 1, so this value becomes 1. So finally what we have is lambda, and this is very important, and this is the final conclusion that we have reached. So this variance 1 is nothing but lambda, and when you want to, and this lambda is nothing but the eigen value, right? So if you want to maximize variance 1, you have to keep the maximum lambda 1, like the maximum eigenvalue. So the maximum eigenvalue and the corresponding eigenvector is going to be your PC1. I promised to explain this equation 1 and why directly we get this value. So now let us try to understand that and try to find out. So if we have this spare page. Now let us try to understand that. So we were having the Lagrangian as b1 transpose s b1 plus lambda of 1 minus b1 transpose b1, and you see b1 is nothing but a 1 cross d-dimensional vector, right? This s is nothing but a d cross d-dimensional vector, and this b1 is d cross 1. So finally this value is nothing but 1 cross 1 value. So this is not, the final value is not a matrix anymore, it is just a 1 cross 1 value. So when you do the del of L, it becomes del of B1t. And so what we are doing, we are keeping B1t as B1 as A into B, and we will try to use the chain rule. So B1 is A, and this rest of the part as B1 is B. So we are applying the chain rule, and we will get B1t d as B1. And for now, let us keep this aside for now. So we are not going to, sorry, we are not going to use this part for now. We just try to understand the differential of this part, because once you understand this one, this becomes very straightforward. So db1t, and this becomes sb1 plus b1t, and s can be taken out since s is not dependent on b1. So s could be considered as a constant with respect to b1. So you can write it like this. And now this is this is nothing but these both values are scalar, as I explained earlier, that this is nothing but a 1 cross 1 value when you finally simplify it. So these two are constant, these two are scalar, not constant, sorry. These two are scalar, and if you have a scalar, then you know that a scalar is equal to scalar transpose. Now let us use this relation to decompose and utilize in this equation. So I will write del of Lagrangian is equal to dB1 transpose into SB1 plus, I will like to transpose the second term, and as we know, if we have A dot B transpose, then we can write it like B transpose and A transpose. So we will utilize this, and further we can write it like SB1 plus, sorry, this is going to be dB1 transpose, and then S transpose, and then B1 transpose. So when you take transpose two times, then it becomes itself. So we can write it like del of Lagrangian is equal to dB1 transpose SB1 plus, this term is going to become dB1 transpose, and this st will remain as it is, and then this is going to be b1. And now, so see, this one and this one is same, this and this is same, the only difference is s here. So what we are going to do is, we can prove that s is equal to s of s transpose. So how we can prove is, like, s is a covariance matrix, right? So you know that covariance matrix is a symmetric matrix, and a symmetric matrix has a property that A is equal to A transpose if A is symmetric. So we utilize this, and we can say S is equal to S transpose, and then we can write it like dB1 transpose into, sorry, this could be written as two times of, I write st as s, then this could be written as s b1 and when you bring this to this side, left hand side, then it becomes like 2SB1. So this is what we wanted to achieve, right? So you will see that this is what we wanted to achieve, right? This is what we wanted to achieve. And similarly you can do it for this part as well, and you will find that you will get 2 lambda p. So that is it. And also I would like to answer one more question, that how it is implemented in actual code. So you will see that if you want to apply PCA, then you are going to compute the covariance matrix, right? You need to compute the covariance matrix, which is a d cross d, and then after computing the covariance matrix you need to find out the eigenvalues and eigenvectors, and then you will try to arrange those eigenvectors according to the magnitude of their eigenvalues. Like the PC1 will be the eigenvector with the maximum eigenvalue, and I call it maximum in terms of magnitude. Then you will arrange PC2, and similarly it goes like that. So it is always going to be a difficult task and a compute heavy task to calculate the covariance, and then after that you will be calculating the eigenvalues of that covariance matrix. So imagine you have a 10,000 dimensional uh, uh, data. So get you want to make this data to 1000 dimensions. So in that case you are going to first compute the covariance matrix for 10,000 cross 10,000 matrix, and once you have this matrix, covariance matrix, then you are going to calculate the eigen values and eigenvectors of that 10,000 cross 10,000 matrix. Imagine how compute heavy is this task. So in practical aspects we do not use this. So in practice, and even in scikit-learn or any other library where you can calculate the PCA, in those library we do not use this kind of setting. So it can be used when you have a data with less dimensions, but it cannot be used directly when you have a high dimensional data. So in that case, how it is implemented in code. So the first one is SVD. So SVD is not a very efficient way, but you can use it SVD, and even SVD fails when the dimensions explode, when the dimensions go beyond certain limit. So even we cannot apply SVD for those cases. And then there comes the power iteration, and there are many algorithms like this which are used in the actual code. So let me know in comments if you want to understand these kind of algorithms which we apply to compute the principal components in an efficient way. Thank you very much for your time, and I hope this video helps you to understand PCA.